So I guess a bit of context about me. So I'm now a lecturer within the School of Engineering. But I remember back when I was 17, 18, I really, really, really wanted to do medicine, but was absolutely petrified by the idea of engaging with patients. So I was sort of looking for something that was applying maths, physics, and chemistry. And my dad said, well, why don't you do mechanical engineering, which is what he did. And I was like, no, that's not for me. It's just not for me. And my views of engineering and indeed general views of engineering are certainly not as sort of stereotyped as I thought. I mean, I was petrified that it would involve soldering and that it was all dirty and workshops and things that I wasn't very good at. But I think there is this perception that engineering is all about physical things. It's about feats of design, like bridges. It's about optimizing planes. It's about turbines. It's about electronics. It's about fluid dynamics and understanding how we can make cars go faster. And it's about why things break. But we don't generally assume that it can have a medical emphasis. And at that time, I don't think there was degrees in biomedical engineering. It was something you could specialize in, but I just didn't know about it. But what there was a degree in material science. So that's what I did, where I could use materials in order to hopefully along the lines sort of regenerate tissue, ultimately, I hope save lives. So what I've got here is lots of applications where we can use really, really sort of fundamental engineering approaches in order to essentially engineer, repair, replace human tissue. So we've got some of the sort of more traditional applications. So we've got things like our metal sort of hip implants. We've got things like bone plates. We've got applications where if you've got curvature of the spine, we can put in a metal frame to repair that or change that curvature. But there's also lots of other really cool applications where we can actually use engineering, we can use engineered structures in order to regenerate and grow new tissue. So a good example of this is in these central images, we've got a cartilage defect in the knee. So someone played a lot of football, worn their cartilage away, and they've got this defect, which can result in arthritis. It's incredibly painful. And we can come up with a engineered material that we can place into a defect and we're actually able to regenerate new human tissue. We can look at wound repair. So if we've got a severe burn, for example, there's particular engineered structures that we can use in order to repair that wound. And finally, there's massive applications in cardiovascular. So, for example, if someone has atherosclerosis, where they've essentially got a blocked artery, then we can use engineering in order to design a stent that will keep that artery open. And so this is really what the focus of this talk is. It's about how we can apply engineering theory to really sort of support tissue repair, regeneration, and ultimately sort of how this fits into biomedical engineering. So I am a material scientist. I teach all areas of materials within the School of Engineering. I think aerospace materials are absolutely fascinating, but my real research interest is in biomaterials. This is only one small area of biomedical engineering. Biomedical engineering is diverse and vast. During the undergraduate degree, you learn all sorts, but I'm just going to focus primarily on my research, how that relates to engineering more broadly. And then I'm going to give you a bit of an oversight of what studying biomedical engineering involves, and particularly what that involves at the University of Leicester, because we are a new school for studying biomedical engineering. We're recruiting our first cohort now, but we have had research in biomedical engineering for the last 40 years. We work really closely with the hospitals, and actually we've got, I mean, my area of interest is biomaterials, but I haven't been teaching it. We've got experts in their field who are now really excited to be teaching biomedical engineering. But back to engineering tissue. So if we think about very, very fundamental engineering and the idea of carrying structural loads, so essentially weight bearing, then we can consider how we can use engineering approaches to support the repair of a badly fractured bone. So here I've got an example of a very, very nasty fracture of the tibia. So this is your shin bone, and you can see that we've got a disjoint between the two bone parts. So in a lot of cases, bones actually have this really clever ability to repair themselves. So bone is a living tissue, there are cells within it. And if you've got a sort of minor fracture, then we can just realign the bones, we can put it in a cast, and actually the bone will repair itself. But something like this, essentially, there's too much bone loss, it needs some help. And in the simplest way, that help can come in the form of a bone plate. So bone plates are literally, well, often lumps of metal, and so they're plates and screws that are screwed into your bone and hold the bone together. So orthopedic surgery is very much manual. Imagine DIY. They have drills, they have screws, it's all very sort of hammers and rough and ready, but it does a job. So these plates are designed to essentially realign the bone and hold it in place while the bone is able to repair and regenerate itself. So if we look at these images in the bottom left-hand side, you can see we've got this badly fractured tibia. We're plating it, we're putting the bone plate in to essentially bring all of the bone bits back together. And you can see in this image C that actually we get complete healing of this bone. So it's no longer the bone plate that's carrying the load. We've got this repair of the bone. Plates can be a temporary fixation device. So there may be some of you who've had a bone plate and had it removed, but there are also cases where it's permanently left in the body. And if we've got something that's permanently left in the body, then obviously we need to think carefully about what any sort of reactions might be to the material. So when it comes to something like this, material selection is absolutely a key process, as key as deciding the best material for aircraft wing, for example. And so if we're thinking about that material selection process, then we need to start thinking about, okay, well, what sort of environment is our bone plate going to be under? And so, yes, we need to think about, okay, how will our body react to it? Will it corrode in the body environment? Will it induce any sort of foreign body response from the body? But what we also need to think is, okay, just fundamentally, what sort of loading will our bone plate be under? And so what we assume when the bone is first broken is that the bone plate will essentially carry all of the load that the tibia bone would otherwise have carried. And so to a simple approximation, we can say, okay, our shin bone is just under what's known as a compressive force. So as we stand on our leg, then hopefully you can all see that actually half of your body weight will be carried in each tibia bone, assuming that you're sort of standing on two legs. That's obviously applies if we're standing, but if we're not standing, if we're walking, running, whatever, then we've obviously got probably more loading than just that body weight. And so let's first of all consider, okay, what is that load that's on our tibia when we are standing? And so we can use a really simple calculation, the sort of thing that those of you who certainly have done or doing A-level physics, probably those of you who are at GCSE, who did physics at GCSE will have covered. So we can assume that we've got a person of average mass, so let's say 62 kilos. And if we want to go from a mass to a weight, then obviously we need to multiply that mass by the acceleration due to gravity. So we can say that their weight is 607 newtons. Okay, so that we could say, I said that half their weight, if they were standing, would be going through one tibia bone. So we'd got about 300 newtons. But what about if we're considering the peak force that we get during gait? So I've got a poll for you here. So we're talking about the peak force through a single tibia during walking. So do you think that that peak force is 2 times the body weight, 3.5 times the body weight, or 4.7 times the body weight? Have a guess. There's honestly, it's not the sort of thing anyone would necessarily know at this point. It's just to sort of get you thinking about, okay, what are the loading requirements on our on a bone plate or on our bones?
We've got lots of answers coming in
Brilliant.
so far. We've got five have said 2 times the body weight, 14 have said 3.5 times the body weight, and three have said 4.7 times the body weight. I'm just going to end the poll now. Okay, so the most popular was B, and then A, and then C.
Okay. So this is one of those things where you can get a lot of different sort of, depending on how the analysis is done, there's varying values proposed, but it is fairly commonly seen that you can actually get 4.7 times the body weight in a single tibia bone. So clearly we've got a lot more than that 600 newtons weight. And so you can see that in this case, if we've got someone walking on that bone plate before that bone has healed, then we need that bone plate to be able to actually hold close to 3,000 newtons of load. Okay, so that's useful, but is it enough just to know what sort of force our bone plate is going to hold? So I've got a really sort of simple thing to get you thinking about here is if we're wearing either stiletto heels or snowshoes in the snow, obviously one of them is going to, the sort of snow's going to hold your weight much better with the snowshoes than with your stiletto heels. And so essentially, as well as the idea of force, we also have to consider the area over which the force is acting. And so that becomes really important when we're trying to decide, okay, what materials can we actually use for something such as our bone plate? And so essentially, if we're thinking now about our bone plate, if we're thinking about the maximum load that it's able to carry, then it has to be a function of both its geometry and its material strength. So we can't just say we need a material that can carry 3,000 newtons, because obviously if we had a material that had a very large cross section, it would be really easy to carry 3,000 newtons, whereas if it was a very small cross section, it would be much harder. And so when we talk about materials properties and material selection, and to be honest, anything to do with structural mechanics and engineering in general, we tend to talk about the idea of stress rather than our force. And so our stress is basically your force per unit area. And so this is then something that we can compare for all sorts of different geometries of bone plates or wing ribs or whatever we want to be looking at. And what this means is that when we're deciding on a material, we could look at what the failure strengths of materials are. So generally, engineering materials have a characteristic strength. There are databases that are full of strengths of materials. And what we've got here is a graph that just shows some of the stress strain behavior of a human tibia. And so you can see you've got various sort of failure strengths associated with these three tibias. One of the things you get with natural tissues like bone is you get massive variation between the mechanical properties between one person and another, depending on age, health, diet, all sorts. What you see in an engineering material is you would generally have a fairly consistent, essentially, failure strength for that material. And so we can use the failure strength that we know of engineering materials in order to say, okay, well, what material could we use in the case of our bone plate? So what we have got here is a really simple sort of approximation of a bone plate. We've just got a cuboid with some holes in it, which we're going to use in order to sort of essentially screw our bone back together. And in order to work out what material we can use for this bone plate, then we need to think about, okay, how strong do we need the material that this bone plate's made of to be? And we can make some assumptions. So a couple of slides back, I said our peak load was, I think, 2,857 newtons or something. Let's just say our peak load is essentially 3,000 newtons. So this is one of the big differences between engineering and things like physics, is there is massive value in engineering to do sort of back of the envelope calculations, just to give you rough ideas. And so you tend to see more approximations than you would perhaps in other subjects. So if we didn't have any holes in our plate, so we just had a cuboid, then I've said that our stress is a force divided by an area. So what we mean by our area in this case is our cross-sectional area. So we are assuming that this bone plate is being compressed, so load is being applied on the top and it's getting squashed. And so the area over which it acts is our cross-sectional area. So in this case, it's our 0.7 centimeters by our 0.4 centimeters, which means that if we work out what the stress on our bone plate is, we get this required compressive strength of 100 megapascals. That's assuming we didn't have any holes. I now get on to something that you would learn about when you do an engineering degree, let's say. So when we have holes in a plate, it not surprisingly results in a concentration of stresses. So you tend to find that around the holes you have a higher stress than that sort of applied stress. And you're just going to have to take my word for this for now. But what you get is you get a stress that's 3 times the applied stress at the edge of the hole. And now this is independent of the number of the holes or the size of the holes, assuming that the holes are small compared to the diameter of the plate, which we're slightly pushing that assumption here, but let's go with it for now. And so if we're saying that without the holes, oh, sorry, if we're saying without the holes that we need a required compressive strength of 100 megapascals, if we've got the holes, we're saying, okay, the stress is actually 3 times that. So we need a material that's going to be able to carry at least 300 megapascals of stress. Okay, so now we can come on to some of the materials that we can use for bone repair. So there are probably 50,000 engineering materials that we can choose for applications. But when it comes to materials that can be used in the body, this list is obviously very, very sort of strongly limited. And that's limited because when you put anything into the body that is essentially foreign, the body will react to it. The nature of the reaction will affect whether the material is just going to get rejected, whether will get massive sort of infection and sort of inflammatory response and essentially a need for other surgery, or whether it is accepted and we can get healthy bone repair. So what I have listed on this table is probably 4 of the most common materials that, in terms of how the body responds to them, are really are fairly well used and respond well within bone. So I've got another poll for you here. So here I've got a ceramic alumina, I've got a titanium alloy, we've got 6000 series aluminium, so that's just a specific aluminium alloy. We've got stainless steel. And what I am interested in is, okay, all of those materials have a compressive strength that is higher than 300 megapascals. But based on this information here, which of these materials would you use for our bone plate?
Quite a few answers coming in. I'm going to end the poll in three, two, and one. Okay, so the most amount of students have gone for D, stainless steel. We've had a tied second with A and C, so the ceramic alumina and the 6000 series aluminium, and then the titanium coming in last.
Okay, that's really interesting. So yeah, looking at that, you might think, well, clearly you might think, well, I want a high compressive strength, so that alumina looks amazing. You might think stainless steel, I know that it's cheap, that's a good choice. And yeah, we've got other options here. But what I'm really trying to show, we can never just consider a single materials property. And what we want from a materials property can vary quite a lot. And it can also vary depending upon the application that we're choosing the material for. So when we look at that first column that I showed you in terms of compressive strength, we see that alumina was the highest and our aluminium was the lowest. And that's one materials property that we need to consider. But there are other things that we need to bear in mind. And one of these is essentially how tough the material is. So how prone to it sort of shattering it might be. And so you can see that with our fracture toughness, whilst our alumina is very, very strong in terms of that compressive strength, it is very brittle. So it's very glass-like in nature, very easy to break. Whereas our stainless steel has an incredibly high fracture toughness. So this fracture toughness column would really sort of emphasize and go along with those of you who said stainless steel. Yeah, it's obviously our best material. So they're two of the materials that we need to consider. But a third property that we have to consider is our modulus. So I guess quite a lot of you will know all about Hooke's law and this idea of the relationship between stress and strain. So what the modulus is basically a measure of how stiff a material is. And for lots of applications, we want a really, really stiff material because we want to make sure it doesn't bend or change shape. But I said earlier that bone was a living tissue and it's able to repair and regenerate itself. Now, that is really, really good, but one of the issues with bone is that if bone isn't loaded, so for example, when an astronaut goes into space, if that bone isn't being loaded, then those cells stop working. The bone no longer repairs and regrows itself, and we actually get bone wastage. Your bone sort of density reduces. And so when it comes to a bone plate, we don't want it carrying all of the load. We don't want it being really, really stiff. We need the bone actually to see some sort of load, some sort of deformation, so the cells are able to effectively repair itself. And so we might not necessarily want a high modulus. We may actually want quite a low modulus. Okay, so you've now got a bit more information around materials properties. So what I'm going to ask now is, okay, with all of this information, which material would you now choose?
Okay, so we have had a winner with stainless steel, and then it goes down to the 6000 series aluminium, and then the titanium, and then the ceramic alumina.
Okay, so I'm really pleased that you've all realised that that low fracture toughness of alumina is now a massive downside because we don't want our bone plate to fracture as well as our bone. We want it to be sort of nice and ductile and not fracture. Um, Stainless steel, yeah, it's amazing in terms of fracture toughness. But actually, what we find when it comes to repairing bone is this modulus value is actually really important. And we want that modulus to be as low as possible. So, actually, what we typically find in bone plates is they are either produced from aluminium or titanium 6-4. Generally, if it's a temporary device, we'll use aluminium because it's cheap. If it's something that's going to be in permanently, then titanium is used just because it has a slightly reduced immune reaction. So any foreign body gets some form of immune reaction. It's just whether it's enough that the body can cope with it or not. So whereas you may have looked at the compressor strength and thought, well, why would we use aluminium or titanium? When we get this whole picture, hopefully you can see why we would use either titanium or aluminium. Okay, so in that analysis, we had a very simple geometry, and I could tell you that holes had a stress concentrating effect, and we could do a sort of back of the envelope type calculation. But if we have complex geometries, we can't do that. Essentially, if we've got something like this, which is actually taken from a CT scan of a wrist, it's your scaphoid bone, we don't have a regular cross-sectional area, so we can't do that simple force over area. Instead, what we can do is we can use engineering tools. We can split up our complex geometry into essentially a set of elements known as a mesh, and we can use a computer software that will give us our stress concentration. And there is a lot of scientific literature out there that looks at this more complex modeling of stress distributions in bone plates and bones. And there's a lot that looks about, for example, in these central images here, we can see how if we have bone versus a composite bone plate, which has a low modulus, and a titanium bone plate, you can see that actually you get much more loading in the bone, and that's actually beneficial with that lower modulus. And so one of the pieces of software that we use at Leicester for our engineering degrees broadly, but it also has massive applications with Biomed, is something called Console. And so what this allows us to do is we can use CAD to create our geometry. We can mesh our geometry, so split it up into those elements. So the computer software can then say, okay, well, what is the stress in each of these elements? And we can get a stress distribution for our, in this case, our bone plate. And you can see that we've got bits of red that are surrounding our holes, and that we've got a peak stress that was 390 megapascals. So this is the same ballpark as that rough hand calculation. Okay, so that was very, very basic structures that are used to repair bone. There are also applications where we can use very state-of-the-art structures in order to replace bone. So good examples of these are knee and hip joints. So there's been a long and successful history in replacing worn knees, broken hips with these metallic implant structures. And there is still a lot of development ongoing in order to essentially allow people to maintain their mobility for longer and longer. We can also get sort of maxillofacial, so jaw reconstructions and things where it's most effective to replace the jaw, and we can use patients' own scans, and we can get sort of very personalized implants. There's also plenty of examples around heart valves, meniscal implants, for example. But tissues are really complex. If we're using a lump of metal, it's ultimately one material, it's the same mechanics throughout, it's isotropic, it's just not tissue. It also, however much we try and optimize the material, it is considered to be a foreign body, and we will get some sort of reaction to it. We can also, if we've got moving parts, get wear particles. And essentially, a major limitation is that our implants are too stiff, the tissue around them isn't loaded, and so we get actually reduced function of surrounding tissue, and it becomes more and more likely that you're going to get more failure afterwards. And so instead, there is a real drive to actually, rather than just replacing tissue, can we use engineering methods in order to regenerate tissue? So I said bone had this ability to repair and regenerate. And that is also applies for essentially the majority of tissue within the body. If a tissue has a blood supply, then generally it is able to repair and regenerate. But for each tissue, there's what's known as a critical size defect. So essentially, if the gap is too big, then it's just not able to repair itself. And it also tends to repair itself with sort of not very nice structured tissue. So if we have a big defect, essentially what we can do is we can provide a scaffold to fill that space, and we can design that scaffold such that the tissue will know, it will see it, and it will think, okay, I need to regenerate. So here, for example, we've got cartilage. It can think, okay, the scaffold's promoting the formation of cartilage tissue. And this is all something known as tissue engineering. So this really is that interface between engineering and life sciences in order to regenerate human tissue. So essentially, what we do, we take some sort of carefully engineered scaffold structure, we combine that with human cells. This might be something that's carried out outside of the body. It may well be something where we've just implanted that scaffold within the body and we've let it sort of do the work in situ. And over time, we are able to regenerate healthy human tissue. And so that is really where my sort of research interests lie, and where there's some really, really exciting advances within biomaterials. And so my perspective on this is really that as a scientist or engineer, we can't ever compete with nature. We can't get the complex structures that we see in nature, but we can take inspiration from it. And so we can look at, for example, bone or cartilage structure. We can think, okay, what are the key structures? What's the chemistry? What do we need to try and replicate in order to provide the cues that body cells can think, yeah, this is what I need to regenerate the tissue. So we can always take advantage of the fact that the body has a capability for self-repair. And so I look at biomaterials as really a scaffold template that can allow the own cells to carry out the repair and regeneration process. And so there is a massive body of research around just considering the structures that we can use that most effectively regenerate tissue. So what I've got on this slide actually highlights some of the undergraduate work that I've been involved with. So these are students that were doing mechanical engineering degrees, but had an interest in biomedical engineering. And they were looking at various metallic structures for bone repair and looking at how we could better model or better mimic the mechanics of bone in order that we didn't get that sort of bone loss that I've talked about. So we got a similar modulus to bone, but also provided a structure that cells were able to travel through it and we could get sort of that tissue regeneration. But that's metals. It would be really good if we don't have to use metals, that we have materials that don't use any cause any sort of foreign body reaction, and that really are designed to encourage that tissue regeneration. The ultimate is that we can use a scaffold material that actually isn't permanent, so that it will degrade at the same rate as the tissue is formed, and our final result is pure, healthy, regenerated tissue. And that's not something that's sort of a pipe dream, it's something that is perfectly possible. And so my research often involves a material known as collagen. So this is a protein, the major sort of organic component of living tissue, and we can engineer it in various ways in order to mimic specific sorts of human tissue. So what I've got here is an example of how we use collagen in order to replace the meniscus. So the meniscus is a sort of semi-lunar shaped bit of cartilage within the knee. Traditionally, you get a meniscal injury and they just take out the meniscus, which is fine until 10 years later and you've got severe arthritis because there's nothing sort of protecting the underlying cartilage. So instead, we're looking at taking inspiration from the meniscus structure, combining fibers and a matrix structure, and incorporate or understanding how the cells are able to travel through this structure, how they're able to lay down tissue, and how this structure will degrade over time. And so the idea with something like this is the implant could be put in there. It would provide some initial sort of biomechanics, but over maybe 12 months, it would degrade. And the result would be we'd got the regeneration of new meniscal tissue. So I have taught quite a lot about just one area of biomedical engineering, essentially because biomaterials is what I know. And that's one of the things that um, biomedical engineering at Leicester is a real advantage, that we have people with all sorts of expertise across the whole spectrum of biomedical engineering, which is vast. I mean, what I've got here is just a summary of what sort of I think biomedical engineering is and how it is really so valuable to society. It really is something where you can make a real difference to people's quality of life and ultimately save lives. So, biomedical engineering is all about medical devices. It's all about understanding what is going on within disease and essentially using engineering in order to improve people's lives. What you might do as a biomedical engineer is vast. It can be entirely computational. There is an awful lot of research ongoing about how we model sort of various scenarios in the body, how we consider, for example, how blood flows through your heart, how disease affects that blood flow, and how we can try and sort of mitigate disease. Being a biomedical engineer is all about collaborating with clinicians. It's all about working with those doctors, physios, full spectrum of clinical practitioners, as well as chemists and biologists, in order to understand how we can engineer structures, how we can use engineering in order to explain biological processes. So I'm a biomedical engineer. I mean, I didn't realize I was a biomedical engineer until, to be honest, I came to Leicester. Before Leicester, I thought I was a material scientist, but I absolutely am a biomedical engineer. Yes, my focus is on biomaterials, but I obviously teach. I work very closely with clinicians throughout Leicester, and that is really how I get the most satisfaction and actually achieve the most from my research is actually talking to them and saying, well, what were you looking for? I think this is an idea, but what do you think? And so it really is a multidisciplinary field. There are all sorts of jobs that you can go into with biomedical engineering. And I mean, these are just the sort of specific biomedical engineering jobs. So everything from a sort of biomaterials developer working for a medical device company or a pharmaceutical company, that you can work within the NHS. There's medical imaging specialists. There's all sorts of sort of biomechanics work and bioenvironment. There really is a whole spectrum of careers, from the sort of very hands-on and practical to the computational to the sort of much more patient engagement, clinician engagement. And obviously, there's nothing to stop you doing biomedical engineering and then going to work for an aerospace company or going into the city. It really does open a whole host of careers. So, just very quickly at the end, focusing on a bit that specifically talks about our biomedical engineering degree here at Leicester. So we offer a 3-year BEng or 4-year MEng degree. Both of these offer the possibility of also having either a year in industry or a year abroad. Our engineering degrees are really about practical skills, expertise in engineering, but also integrating that with that sort of understanding of physiology and disease. It is very much sort of technology focused. It's understanding how you can develop medical technologies that really are valuable for diagnosis and treatment of disease and in sort of supporting treatment. So the 3-year program really sort of gives you that comprehensive overview of both engineering technology and that life sciences knowledge that allows you to build that technology and those medical devices. What we additionally offer in the final fourth year, that MEng, it gives you a deeper understanding of human biology, of some of the sort of more innovative, really state-of-the-art technology in terms of rehabilitation diagnostics. But it also gives you much more of an understanding of the sort of project management and the sort of process of getting to market. So, in terms of what our degree looks like, so at Leicester, we have a core first year for all of our engineering degrees. This means that you could come in saying, okay, I absolutely want to do biomedical engineering, but you might decide, well, actually, I want to do aerospace. Equally, we're hoping that people will come in doing aerospace and think, yep, I've done all of this fundamentals in year one, but actually, year two, I'm going to change on to biomedical engineering. It is a core year first year, but we will give you some sort of clinical and biological sort of input in that year one, three sort of non-examinable modules and content. Year two, this is really where we start that focus on biomedical and medical technology and how it's all about that practicality of, okay, what do we need to do to develop this technology and how do we get it to market? You will build expertise in sort of biomaterials, things like control, understanding about prosthetics and things, mechatronics, how we can use embedded systems, and getting that fundamentals of human anatomy and physiology so you understand what it is we require from that medical technology. And you'll also work on a medically related team design project at that point. Year three, we continue that sort of combination of state-of-the-art engineering and the sort of understanding of biomechanics and biofluids. And so you'll have that overall picture of how we can go about building innovative healthcare. Year four, it's much more of that sort of real state of the art, the leading edge. You will also get this opportunity to sort of build a healthcare technology as a group project, working alongside clinicians and medical students and getting that picture of how we sort of bring medical technology to market. Okay, so obviously I'm doing this to sell biomedical engineering, but I'm also doing it to sell biomedical engineering at Leicester. And so I want to emphasize again that Leicester does have a real track record in biomedical engineering. We might be offering it as a degree for the first time, but we've been researching it for the last 40 years. And we have a real breadth of experience in biomedical engineering, from instrumentation to signal processing, particularly around sort of ECGs and things. We have experts in neuroscience, in machine learning, materials, and computational biology. And so you will be taught by experts in their field, and your course will be inspired by state-of-the-art research. We also work really closely with Leicester NHS Trust. You'll gain sort of practical experience with that clinical cooperation. And our projects, your second year design project, individual projects, that fourth year project, they'll all be sort of designed in consultation with clinicians and also with the sort of medical technology industry. And finally, we've sort of, as we've designed this program, we've done it in collaboration with industry, and we've got sort of placement opportunities, and we're really pushing this as a practical degree where you can become a real innovator in biomedical engineering. Okay, so that is the end of me talking for today. If you want any more information around our degree programs, then I've provided the links here. I've also provided a link to the Biomedical Engineering Research Group's homepage if you want to see a bit more about the sort of research that we carry out within Leicester and get an understanding of sort of how that might inspire our teaching in the future. And I am happy to answer any questions.
Thank you for that, Jenny. That was great. If you have any questions, please put them in the chat. We have had a question earlier from Oliver, which I'm assuming is regarding the bone plate. And it's asking about what if the holes are longitudinal, then if there is a similar effect.
Um, so it it will always act as a stress concentration. One of the reasons that it is so appealing to use sort of computational modeling is the value of that stress concentration depends upon the orientation of the holes, how it's loaded, and you can get books of sort of databases around stress concentration factors for various holes and various loading environments. And so if we can model it, it is much more straightforward. So yes, holes do always have a stress concentration, but whether it's 3 or not depends upon the geometry and the environment.
Another question is, do you have any scientific literature which you would recommend?
I mean, there is so much research ongoing in sort of every area of biomedical engineering. Um, I mean, I think a good approach is always to take something like Google Scholar. If there's an area of biomedical engineering that you're interested in, just type it into Google and have a look at what comes out. I mean, yeah, there is new literature coming out every single day.
We've also had another question saying, do you tend to work in hospitals or labs as a biomedical engineer?
Um, so more typically, I guess you probably work in labs. I mean, actually, some of those labs are within hospitals. Some of it will be within sort of medical device companies, within sort of pharmaceutical companies. I mean, within as an undergraduate, you will have labs in biomedical engineering. A lot of those will be in sort of chemistry type labs within engineering. You'll also do some sort of biology type work with sort of cells and human tissue potentially. So I think, and some of the time you'll just be sat at a computer. So I think there's a full spectrum of sort of what you end up doing within biomedical engineering.
We've had two similar questions, so I'm going to combine it into one. But what type of work experience would be useful, or what is enough work experience?
Um, so I think biomedical engineering isn't something that it is very easy to get work experience prior to university. It's something that health and safety often sort of requires that often you're over 18 or certainly heavily sort of monitored. So I don't think when you're applying for something like this, it's about having practical work experience. I mean, maybe having sort of spoke to people, having an understanding of what it involves. But I don't think when it comes to applying for biomedical engineering, there's a need for relevant work experience. It's just having that awareness of sort of what it involves and an interest in it, really.
Thank you so much for attending, everyone. Oh, I've just seen a question. You don't need to have studied A-level physics to attend to go on to the engineering course at the University of Leicester. Um, so that answers that question. But other than that, thank you so much, and thank you so much, Jenny, for hosting this fantastic event.
Brilliant. Thank you very much all for attending.